Example 1. The finite region R, shown in the figure below, is bounded by the curve with equation y equals 4 minus x minus 2 squared and the x-axis. The x-intercepts of the curve are 0 and 4. Use algebraic integration to find the exact area of R. Now, to find the area between a curve and the x-axis, we can use definite integration. So that's when you use integration with limits. And in this case, the limits are actually going to be 0 and 4 because that's the area we're interested in. And we're integrating the curve, so 4 minus x minus 2 all squared with respect to x. Before we actually do the integration, let's simplify the expression inside there. So on the side, we could expand this out. When we do that, we get this. The 4 minus 4 will cancel, so all we're going to be left with is minus x squared plus 4x. We can then take that and replace what's inside the integral symbol. So we're actually going to integrate between 0 and 4 of minus x squared plus 4x dx. When we integrate that, we use big square brackets and we're going to get minus x cubed over 3 plus 4x squared over 2. Close the square brackets, put 0 and 4 on the outside. If you want, at this point, you can simplify what's inside the square brackets. So we could make the 4x squared over 2 into just 2x squared, and then we can evaluate the limits. So big round brackets for this point. Sub in the 4 here, sub in the 0 here. Type each bracket into our calculator and we'll get 32 over 3 for the first one and just nothing or 0 for the second one. So overall, the answer is 32 over 3. Now, because we're talking about an area, we can say 32 over 3 units squared, because we don't know whether this is in centimeters, meters, or whatever, so we just put units squared. Example 2, the sketch shows the curve y equals x, x minus 2, x minus 5. Part A, write down the values of x where the curve crosses the x-axis. For this part, we want to consider when y equals 0, because that's when the curve would cross the x-axis. It's crossing at 3 separate places there. And if we look at the equation of the curve, we can see that y would be 0 if x was 0, 2, or 5. And those are the 3 places where the curve crosses the x-axis. Part B, find the area of the shaded region. Now for these ones, you have to be careful. If you've got part of the area above the x-axis and part below, you need to know that anything above the x-axis will actually give you a positive value for the area, but anything below the x-axis will give you a negative value for the area. With that in mind, to find the total shaded area, you have to split the two areas up and find them separately. So for the positive value area, that's going to be when we integrate between 0 and 2 of the curve. Now our curve equation is this, but let's expand it out first before we try to integrate. So just somewhere on the side, if we expanded this out, we'd get this. And then we can use that in our integral symbol. So we'll bring down x cubed minus 7x squared plus 10x, all with respect to x. We now integrate. So big square brackets, doing the usual integration rules. At this point, it would be 10x squared over 2. So I'm just going to go ahead and simplify straight away to 5x squared, all between 0 and 2. Now evaluate the limits. So 2 to the power of 4 over 4, and so on. When you evaluate this, you get 16 over 3. And that's the positive value area, the area that's on top of the x-axis. So I'll just make a note up there that that's 16 over 3. Now for the negative value, that will happen when we integrate between the limits of 2 and 5. Still integrating that curve. So this part, when we actually do the integration inside the square brackets, that will be identical. All that's going to change is our limits. So instead of 0 and 2, we're going to have 2 and 5. When you evaluate these limits, you get this. And that works out to be minus 125 over 12 minus 16 over 3, which altogether is minus 63 over 4. Again, that's a negative value, just as we would expect because the area is below the x-axis. So let's make a note up there that it's minus 63 over 4. But then to answer the question where we want to get the total area of the shaded region, we need to add those two areas together. So it'll be 16 over 3, and then we're going to plus 63 over 4. So we're going to take the positive value of the area there. When we add that, we get 253 over 12 units squared for the final answer. Just to clarify, we take the positive version of the negative value that we got there because areas as a concept are always positive. Last example, the sketch shows the curve y equals 10x minus x squared and the straight line y equals 2x. Part A, find the coordinates of the points where the line intersects the curve. On the sketch, we can see that there are 2 points of intersection here and here. To find them, we just need to set the equations equal to each other. So to find points of intersection, let's do 2x equals 10x minus x squared. That's because whenever you're finding points of intersection, you need to do simultaneous equations. If we rearrange this, we get x squared minus 8x equals 0. Factorize to find x. This means x is either going to be 0 or x is going to be 8. When x is 0, sub that into either of the original equations and you get y is 0. So one point of intersection is just 0, 0, as we can see from the diagram. And the other one will be when x equals 8, y equals 16. So it's 8, 16 there. Part A done. Part B, find the area of the shaded region. Now this one is interesting because integration will always give you the area between the curve and the x-axis. So if we were to integrate the curve between 0 and 8, we would actually end up finding this whole area here. But that's more than what we want. We only want the shaded part. So what we're going to do is we're going to find that pink area via integration, and then we're going to take away the area of the right-angled triangle here in blue afterwards. And that will leave us with just the shaded region. So if we start with the integration to find the pink area, that's integrating between 0 and 8, the curve equation. So 10x minus x squared. When you integrate that, you get this. When you sub your limits in, you get this. That leaves us with 448 over 3, take away 0. So altogether 448 over 3 units squared for the pink part. Again, that's not our final answer because we don't want to include that blue part on the diagram, which is just a right-angled triangle. We can use the coordinates of the points of intersection to help us to get the dimensions of that triangle. Hopefully you can see it's going to be 16 across and 8 up. So the area is just 16 times 8 divided by 2, base times height divided by 2, or half times base times height, whatever you prefer. We get 64 units squared, and therefore the area of the shaded region that we want is going to be this. 448 over 3, take away 64, which works out to be 256 over 3 units squared. Final answer, and that's it. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already. And do share this with anyone else you think might find it helpful. Thanks, and see you next time.